Pandey, Executive Director, INSA. Ladies and gentlemen, as I can see that all the audience present here are basically college-going students, maybe in the first, second, or third year. Dear students, this is to have the information to you all that INSA is the oldest scientific organization of India, and it was formed in 7 January 1935. That is even before independence. So we are sitting at a place which holds its own legacy, and as recently we know the fact that India also hosted the AI summit. So with all these procedures and proceedings that is going on in our nation today, we are very well aware that science holds a very important position in making India Viksit Bharat. I request the audiovisual to please check for the echo. Thank you so much, honorable dignitaries, for joining with us today. As I was interacting with the students, so I request all of you that you may please search for opportunities regarding science and technology, connect with people, and learn what miracles science can do in future and today, and also making India as our vision of Viksit Bharat. This is indeed my pleasure to now request Dr. Brajesh Pandey, Executive Director, to kindly present a floral bouquet and extend a warm welcome to our distinguished dignitaries. Firstly, we are gratified to have with us Professor Ashutosh Sharma, President, Indian National Science Academy, and Professor Sami Erol Gelenbe, our distinguished speaker for today. Thank you so much, sir. Ladies and gentlemen, I now request Professor Ashutosh Sharma, former President, Indian National Science Academy, to address the gathering with his cognizance. Over to you, sir.
How come there is a delay between what you speak and there? I will. Okay. Well, thank you very much for having me here. This is a great pleasure to welcome our guest today, a very distinguished professor. Is it working? Yeah. Now you can hear that, right? I think you should shut that, shut that part because there's a delay. This is so funny. This is so funny. So you must remember, this is Academy of Science, not of Technology. We need also, we need to have engineering and technology, right? So to cut down the delay, just cut it down. I mean, just remove that. Okay, it's very easy. Turning something on is difficult. Turning something off should be like that. Go ahead, turn it off. Nice, turned off now? No, not really. Okay, great. Chalo. So I'm very pleased to welcome you here, and that we are in for a big treat listening to the lecture. Any of you from MIT University here? Were you in my lecture in the morning? No, you are not. Okay, wonderful. So I can tell you some stuff. And so it's great that this is happening in Indian National Science Academy, and in particular that we are inducting here today Dr. Professor Gelenbe. Um, Indeed a pleasure, and you would all enjoy listening to him because all the fellows of Indian National Science Academy, they are scientists of great repute, have done great work, they have done deep work in their areas, and especially our foreign fellows are elected with great care. So, this is like one in selection. So clearly, we are in here for a treat. And again, thank you, sir, for being with us. And we greatly look forward to your oration. And all of you stay awake, huh? You're going to have some high tea after this lecture. So pay attention, learn something. What I was saying is, look, the greatest skill in today's world and in the future is learning to learn. So nothing is finished. There is no finished knowledge. There is no finished product. Everything is under flux, under dynamic changes which are happening thanks to challenges like sustainable development and rise of intelligent machines. All of this requires that we understand a whole lot of things, but we also put in action what we know and have many different perspectives to bring on the problem. So one such perspective that we want to learn here today, and thank you very much again.
Thank you so much, sir. Dear audience, it is great. It is my great honor to introduce our distinguished speaker for today, Professor Sami Erol Gelenbe. Professor Gelenbe is a globally acclaimed computer scientist known for his pioneering contributions to computer systems, communication networks, and artificial intelligence. He has developed influential analytical models, including the G network model and the random neutral network, which have significantly advanced performance modeling, optimization, and deep learning methodologies. His work spans areas such as network routing, cybersecurity, brain inspired computation, and large scale system optimization with impactful applications in both academia and industry. Today's lecture, titled AI Viewed as Algorithms and Computation for Optimization and Simulation, will explore the historical and computational foundations of artificial intelligence. The talk will trace the evolution from early algorithm concepts and neural models to contemporary deep learning frameworks and will highlight the random neural network as a mathematically grounded model for optimization, simulation, and intelligent decision making across domains such as communication networks, medical imaging, and cyber attack detection. With this brief introduction, I now request Professor Sami Erol Gelenbe to kindly deliver the INSA Distinguished Public Lecture.
Now the next challenge is to make sure my slides are going to work. What I'd like to say as we wait for the first slide to appear is the following thing. I always ask my students when I teach a course, I always ask them, what is the difference really between undergraduate studies and postgraduate studies? I think a lot of the students here are undergraduates. So they look around and they say, well, if you're older, now it's going to be a master's degree or something. I said, no, the big difference is when you're an undergraduate, you think that the professors know everything. But when you become a graduate student, you realize, you understand that the professors know almost nothing. Why is that? Because what we know and what we can say is an infinitesimal part of what we actually don't know. Okay, you take all those things that are around us, and we can explain certain things, but most of the things that are around us still we cannot explain. And that is really what science is all about, realizing that there's always a lot to discover and to find out. Okay? So I'm most honored to be here, and I thank the former president of the Academy for coming here, and I thank all the people who have made an effort to have me here today. I'm really very grateful for this, and I'm very honored. And I'd like, with respect to AI, which is such a kind of a up and coming, lots discussed. It's doing the press all the time, national meetings, and like you've had here, and like there was one in France a year ago, etc. Now, all these things about AI actually try to tell us that it's some kind of magic. Actually, it's very simple, and it can do some things, and it cannot do many things. It can't do most things, and it can do a few. Okay. And I'd like to present to you the material about AI in that perspective, which is why I'd just like to tell you to begin with that machine learning, now we call it AI, but we'll talk about AI a little bit more in a historical context in a few minutes. Machine learning basically does two things. It does heuristic optimization. So models are set up, and these models are optimized to do what? To mimic reality or to mimic data sets. Okay? And the optimization is to minimize the error they may make in representing this reality. And the second thing they do is they do data-driven simulations. So when you use ChatGPT and you put a prompt, okay, and then what is this AI doing for you? It's doing a simulation of an answer to that prompt. Okay, and in this simulation, there are parts which are deterministic, which means that if you ask it the same thing again, it will reproduce the same thing, but other parts which are statistical or probabilistic that will appear differently the next time. And this is for various reasons. One is that in the meantime, the software that you have in front of you, the AI, may have learned something new and is producing something which is influenced by the new information. Okay? And another reason is that knowingly, in certain cases, the system has been implanted with probabilistic generators to avoid boring you with the same thing every time, knowing that one thing is not necessarily the best. Okay, so you have these two aspects, one which is optimization and one which is simulation. And both of these things are well understood activities. They are not new. So AI is bringing these two things together. Now, let's look a little bit further into history, okay, and ask ourselves, where did AI come from? Well, what we call AI was actually coined, artificial intelligence. The term artificial intelligence was coined in 1956. It was coined in 1956 by a person called John McCarthy, okay, who was kind of one of these very good American scientific salesmen. He did some very useful work in areas like time-sharing systems, connected computers, cloud centers, and things like that. But he also organized the first conference that actually coined the term. Okay? And he called it AI. And he was kind of a true believer of AI, which I'm not. I mean, I'm kind of a skeptic. He was a true believer, and he said, well, it is intelligent. These things, very mechanical things, are intelligent, which of course I don't believe in. And the other person who kind of had an influence in this respect is Alan Turing, and you've heard the name. Alan Turing came up with the question of, if you have a mechanical system, by mechanical, I mean a computational or robotic or whatever system, okay? How can you tell whether this is intelligent or not? And he said, well, the test is you take a human being, and then behind the curtain, you ask questions to two objects. One is this robot or this machine or this artificially intelligent thing, and then the other one is a human being. And you listen to the answers, and if you cannot tell the difference between the two, then the machine is intelligent. Okay, that was his definition. While McCarthy was saying everything that has some semblance of doing something the right way and being smart is intelligent. So that is fine. I mean, that's a way of looking at it. However, I think as we go into AI, we must realize that this is basically computation. Okay, and historically, where did this come from? Algorithms. And some of you may know that the term algorithm comes from the name of a person. And this was Al-Khwarizmi or Al-Harizmi, depending on how it's pronounced. Now, this chap had a very nice faculty academic position. He was a full-time researcher and, in a certain sense, teacher in the House of Wisdom in Baghdad. But what does Al-Khwarizmi mean? It means coming from Khwarizm, which was a northern part of Iran, and where there were a lot of people coming from the Silk Road. Okay, so we don't know exactly what his nationality was. He might have been Indian, he might have been Chinese. We never have a photograph of him, of course, and he might have been Turkish from that area. We don't know. Okay, but like a lot of people of his time, he wrote in Arabic. When he was in Baghdad, he used Arabic as his mode of expression, and he had been deeply influenced by Indian numerals. Okay, the notion that a zero exists. So as soon as a zero exists, you have the notion of an equation. This is equal to that. So if I subtract this from that, the result will be zero. Okay, the notion of equal is fundamentally associated with the notion of zero. Interestingly enough, you'd say, well, I mean, quantity zero, is it the same thing as quantity something which is equal? Well, you take the difference. And if they're equal, then the difference is zero. Okay? So that was extremely important. And he developed methods for solving linear and quadratic equations. And he wrote this in a book. Okay? And he called his book the Brief in Arabic, the Brief book, where we discuss about exchanges and equalization in a certain sense. And we reestablish structures, simplify structures, reconstruct structures. And in his book, he has two terms, which aside from his name, there was, one more term in the title of his book that is the origin of the word algebra. And he used the term al-jabr, which meant in Arabic, apparently, the notion of equalization or reconstruction. So reconstructing expressions in equations was what he meant. He was reconstructing the equational results, simplifying equations, and so on. And so algebra and algorithms come from the same source. Now, his work was translated into Latin much later. So he wrote his book in the 9th century. 8th, 9th century was that period, was his lifetime. And the book was translated into Latin by an English priest. Of course, they were the only people who knew proper Latin at that time. And this English priest worked where? Guess, he had to know Arabic. He worked in Spain, where the Arabs, part of Spain there were Arab kingdoms. So he worked in Spain and he did the translation. And for about 2 centuries after that translation, this was the main math book that was used in universities. It was the main math textbook, okay? So this notion of algorithm, which AI uses, machine learning uses, comes from this particular source. I mean, finds its origins in Al-Khwarizmi's work. However, it took a long time to start building real calculating machines. Okay, the first steps towards computers. And the first real calculating machine is from the 17th century. And the person who designed this was 19 years old. And he was the son of a tax collector, Blaise Pascal. So Pascal, his father, had a career which was partially in the town of Rouen. Now, it's interesting to say something about Rouen because at that time it was an important seaport. Being an important seaport, there was a lot of information flowing out. There was a commercial activity flowing in and out. And also there was mechanical capability, because shipbuilding and anything, you had to build compasses, you had to have sextants for sailing and so on. So there was mechanical capability in this city. And he designed the machine, but of course he was helped by workmen to build it, and up to 50 of these machines were built. And about 7 or 8 have survived. 2 of them are in Paris. If you go to Paris, you can see one of them. And this was his calculating machine, okay? And what it did was actually adding and subtracting, essentially. And what was the motivation? It was to help his father, the tax collector, to keep track and not make mistakes, okay, in his calculations. So this is very interesting. But they couldn't make more than 50. Why? Because doing the mechanics of this thing was already a huge effort. So there was so much. I mean, these were handmade, you know, with files and so on, and little wheels inside. So it was non-trivial at that time to even produce the mechanical aspects. Now, the next step, there were 2 things that came along. The first was the so-called difference engine, and the other was the analytical engine. Now, these 2 were designed by the same person, Charles Babbage. And now we have gone forward by more than 100 years since Pascal. And Babbage, and in a few minutes, you will see what the motivation was for this. Okay? Babbage, he was a professor in Cambridge for about 10 years, but he resigned his professorship because as a professor, he would have to teach, and that was taking his time. Okay, he was a professor of mathematics and he had a very prestigious chair, but he said, I'll resign this position, and he wanted to sit in London and build his machines. This was what really interested him, and he did that. And he built 2. One was, at least designed 2. One was a difference engine, which in fact went from the Pascal machine to adding to the machine multiplications, essentially, okay, and inversely divisions. But that's how it was. And the second one was the analytical engine, which he designed on paper, essentially, and only parts were built, and which is essentially what today's computer is. It is a stored program computer. And he had all the ideas that then were put into motion when, during the Second World War, for the Manhattan Project by people like von Neumann and so on. So what's very interesting is that Babbage had really the idea of what a computer should be. Now, for the motivation for this, it's rather interesting. I will come to it in a minute. Now, Babbage went to, he lived in London, and he was invited by the University of Torino to give some lectures. Why Torino? Torino because it had a very good mathematicians there associated with the Kingdom of Savoy. Torino was the capital of the Kingdom of Savoy. And the Savoy Kingdom was high-tech because the dukes first and the kings later were very much involved in warfare. The Duke of Savoy was one of the military commanders, typically the military commander of the Austrian Empire, one of the important. And then they fought the Austrians. Why? Because they wanted to take over Italy. So by the time of Babbage's time, the Kingdom of Savoy was engaged in a competition with Austria for the control of northern Italy, and was in competition with the Pope for the control of central Italy, and in competition with the Bourbon family, who had been kings of France and who had been kings of Spain, etc., for the control of the south of Italy. So he had a huge competition on his hands, and the teaching in Torino was of high quality, and had famous mathematicians like Lagrange and some other, Peano for number theory, Lagrange. These are big names in mathematics, and these people were professors there. So he was invited to give a talk because they said, well, what's the guy doing? And his talk, in fact, let me go one step down, was written down in French. So he was speaking probably English and French. Babbage probably knew French as well, so he's speaking English and French. His talk was written down by an engineer, Luigi Menabrea. This is something that people don't usually say, because people give all the credit to Ada, Countess of Lovelace, but in fact, who was a daughter of Lord Byron. But so you see the two of them on this picture. Luigi Menabrea wrote down the talk, the presentation, okay, and a lot of the comments. And Babbage talked about his machine, but he also talked about programs, computer programs as you understand them now. He would write them in English, instructions, and the machine does this and the machine does that. But his instructions were interpretable, directly interpretable by the machine he was designing, that he had designed. Okay, so he did that, and this was published. Menabrea's article on the talk was published in Geneva. Which was a big printing center. Again, there are interesting reasons for everything. Why Geneva? Because it was a Protestant city, and the Protestants were open to knowledge. And they couldn't do things in Rome because the Pope would say, well, this is not right for the church and so on. But Geneva, it was a Protestant city, so it was a big printing and publishing center in Europe at that time. So he published it in Geneva. And then Ada, Countess of Lovelace, who was Lord Byron's daughter, translated it into English and added some notes. Okay, so what we know about Babbage's machine is essentially from Menabrea's article. Okay, all the details, and of course, a lot of the plans for his machine still exist. He was a very detailed planner, so we know that he had the concept of computers. Okay, so here you have all the information, and then a little further political element. You might say, what was the motivation? Because Babbage also got at that time something like £1,700 from the British government to do the design. Okay, so what was the motivation? Well, the French, of course, who were at that time one of the main competitors of the British in Europe, and sometimes the enemies, okay, long wars between the British and the French government had a project for doing very detailed analysis and census type things. And the idea behind Babbage was that he thought he could partially automate this with a computer program and running on his machine. Guess what the other interesting aspect of the Babbage machine is? Today, you hear that AI is taking a lot of electricity. Okay, Babbage thought he needed a mechanical driver for his machine, and he thought he could do it with a steam engine. There was no electricity production in the sense that we understand now at that time, and he thought that he would have a steam engine turning the cranks around, and the machine would chug, 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 and do the computations automatically. So very interesting, all of this. Okay. Now, there's one thing I'd like to stress here on this slide, and I will read what Ada, Countess of Lovelace, wrote down. It's known as her objection. It is desirable to guard against the possibility of exaggerated ideas that might arise as to the powers of the analytical engine. In considering any new subject, such as AI, there is frequently a tendency, first, to overrate what we find to be already interesting or remarkable, and secondly, by a sort of natural reaction, to undervalue the true state of the case, when we do discover that our notions have surpassed those that were really tenable. The analytical engine has no pretension to originate anything. It can do whatever we know how to do, to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relation or truths. So this is basically the same thing as AI. Okay? So what it does is it takes a lot of data that is coming in and approximates it, reproduces it, but doesn't generate new knowledge or anticipate the future. Okay, so we have to be kind of a bit realistic about all of these things. The next things I was going to talk about are perhaps less important, even though I was going to talk about undecidability. But just let me mention that it was already proved by two different people. The first person to prove this was someone called Alonzo Church. And the second person was Alonzo Church's student, Turing. Alan Turing was a student of Alonzo Church. Church was a professor at Princeton, a professor of logic. And Alonzo Church proved that any formal system, any formally defined system, if you take one of those and ask it to say whether some other formal system can do a particular job or not in a finite amount of time, that is impossible, that it doesn't have the ability to kind of pass decisions regarding what another formal system can do. Now, this is called the undecidability problem. And it was first shown by Church. And then Turing, who was familiar with the analytical engine, with Babbage's design, he built a formal model called the Turing machine, which is actually a mathematical representation of the machine that Babbage had designed. And he proved that this machine cannot be used to decide about other similar machines, whether they can do a job or not. Okay, the undecidability problem of Turing machines. So that was quite interesting. Now, very widely used neural network models don't come directly from this, from what I've just said. They actually are equivalent. Okay. However, they typically use a different model, which was a model of basically neurons. And this was set up. I mean, the neural network models that all of you use, the CNNs and so on, they're basically the model of Warren McCulloch and Walter J. Pitts. So these were kind of weirdos in those days. They were people who didn't really have good positions. Okay. They didn't even have great careers. They probably died frustrated or unhappy in a certain sense. Okay. But we are all these people who are now making millions or billions, it's whatever around this, they're living off what those guys did. Okay, McCulloch and Pitts. But they were not the first to come up with this idea of neural network. And the first work that actually brought the idea of a neural network up front was the work of Golgi, who was a professor of medicine at the University of Pavia, and who got with another person at the same time as another person, Ramon y Cajal, a Spanish person, who received the Nobel Prize in Medicine in 1906, Physiology and Medicine, for their work on neurons. So Ramon y Cajal had the notion of a single neuron, and he studied that, and Golgi had discovered techniques for dyeing tissue so that he could see the neural network under the microscope. Okay. So these two people, and the other thing about Pavia is Pavia was also the university where bioelectricity was first studied by a person who gave his name to the volt. 220 volts, 110 volts. Well, the name is Volta. He was a professor of physics in the same university where, much later, Golgi was also a professor. So you see this continuity with knowledge and the kinds of problems that people ask themselves in research. So this gives you a brief passage. And then I need to mention who was the first person who came up with something like ChatGPT. Okay? And this was a person called Joseph Weizenbaum, who emigrated from Germany in the early 30s, I think, in around 33, 34, some years like that, with his family. He came to the US. They were running away from Germany, and he had not such great studies, so he didn't go to a great university. He went to Wayne State University, which is kind of the bad copy of the University of Michigan, Ann Arbor. So he went there as a student, and then most of his career was at MIT. And Weizenbaum designed ELIZA. ELIZA was a ChatGPT specialized in psychotherapy. So, it wasn't a perfect psychotherapist, but basically you could, it mimicked what a trained psychologist would say to a patient. who said, well, I have this problem and I'm afraid I can't go into the dark or whatever, the kinds of things that a person with psychological problems might say. And Eliza would answer. Okay, and inside was a very simple pattern matching algorithm. Well, if he said this or she said this, then I will say that. Then I will come out with that pattern, and was doing this. And this was really the first chat GPT kind of system. And of course, this was back a long time ago in the 60s, late 60s. Okay, so you see that nothing is completely new under the sun. And now we have more elaborate systems like that. So he was the first to demonstrate that. And towards the end of his life, he went back to Germany, and he spent the last 10 years or so working in Berlin, back to his hometown where he had been born. So that's kind of interesting. The other person we owe a lot to in this field is John Werbus, whom I met, and met many times. He was the person, you're all using backpropagation, the backpropagation algorithm or something like that. He was the person who actually showed that backpropagation could be used for these neural network models of the McCulloch and Pitts type. So he in his PhD thesis, he talked about that. He got some recognition, but never a huge amount of recognition. And I'm sure he's not a billionaire, hasn't gone after those things. But for a long time, he was helping others because he was heading a research group at one of the American research funding organizations called the Office of Naval Research. I even got funding from him when I was starting my work in this field. And he supported and helped other people do research on neural nets and machine learning and so on. And he himself, at the beginning, had done quite a few very important things. And I always remember him with a smile. He'd always come along and smile slightly in a relaxed way. Yeah, you can do this, you can, kind of thing. He was that kind of person. He's that kind of person. Okay, now, what did I say? I said there are two things that actually all these machine learning tools do. One is optimization, okay, and the second one, but heuristic, you don't necessarily get the global optimum or global minimum, or even you don't even guarantee that you're going to get so-called local optima or local minima. You're getting something which approaches them, but you never know in a very large computation whether you reach any of those and exactly where you are. Just know the numbers that you get, okay? And what is the purpose of this optimization? It is to match, to minimize the difference between what your machine has stored and the data it's representing. So it's a form of function approximation, okay? And all the neural network models that we use have to be shown to minimize, to be, if you wish, universal approximators for continuous and bounded functions. That's the kind of property that people show. And the first person to show that, I don't have a picture of him, is Lee Giles. Lee Giles, who's still around, he used to be at Dartmouth. He's probably Dartmouth College. He's probably still there. And he's the person who actually proved that the McCulloch-Pitts model is a universal approximator for continuous and bounded functions. But the basic idea is if you're going to do optimization, you must be able to calculate derivatives. Okay? And that kind of, you can do it heuristically, completely heuristically, but if you can calculate derivatives, you can see in which direction you should go to minimize or maximize a function, okay? So you need to be able to calculate derivatives. And all of these, neural network algorithms have derivative calculators inside. You're probably using like a black box, a piece of software that does things for you, but it's calculating derivatives, whether you like it or not. And these derivative calculations, you have to find a way to make them efficient. So in my slides, and I will be leaving my slides with the Academy, so they will do what they want with perhaps put it online with my talk. But the derivative calculations are exactly carried out so that you can see them. And of course, to calculate derivatives, you must find a clever algorithm which will simplify the derivative calculation. And it turns out that with the so-called sigmoid function, as well as with a random neural network that I will show you in a few minutes, you can show that basically you have two operations that you're carrying out systematically. One is you have a nonlinear relationship. And this nonlinear relationship, you calculate a fixed point. And the second thing that you do, fixed point means a solution of a function of the form x, of an equation of the form x equals fx, or f equals gx, and g is a nonlinear function. So you have to do that, and x is a vector. Okay. For instance, x is a vector related to all of the neurons in the network. So you have to be able to do that, a fixed point solution, and then what you do is a matrix inversion. So, and the matrix inversion is actually what backprop is. So you have this repetition of steps, okay? And the more you do, the closer you try to get to the minimum. Okay? So that's, or to some minimum. If you're doing, if there are multiple minima of a function, then you're trying to get to one of them. So that's what these steps are actually doing. So that's interesting. And now, as we move forward, let's see how we're doing for time. Probably getting close to the end. What's kind of interesting is this McCulloch-Pitts model doesn't really, the one that you are all using, doesn't really capture the way the brain works. Okay, and who knows how signals propagate in the brain? Who knows that? Well, neuroscientists do. Okay, and for a long time, this was kind of a hard thing to do. Golgi, for instance, I said he got the Nobel Prize. He was a neuroscientist. He was a medical doctor, but he was dealing with brains and looking at the brain structure. Okay, and if you go a little bit further in time, the big difficulty of knowing how the electrical signals propagate is that to be able to measure the electrical signal, you have to put in a probe. This probe needs to be metal to pick up the signal. Gold, for instance. You need a probe made of gold. But as soon as you put a probe made of gold, even very small, what do? You create short circuits. Where? In the brain. Okay? So what they had to do is create probes which were gold filament, okay, very thin gold, covered by glass. So getting that technology right was a long process. And along comes Terry Sinofsky. Sinofsky arrived with the right knowledge at the right time. He's a physicist. He got his PhD under someone very well known called John Hopfield. Sinofsky worked with John Hopfield and initially in statistical mechanics. And then he went to do a postdoc in neuroscience. I don't know exactly for what reason. I have met him, but I didn't ask him his reasons. He's now a professor in San Diego at the Salk Institute, which is a biological institute in San Diego. And there, doing his postdoc, he actually did the first detailed measurements of brain spikes. The real signals are in the brain that you see down there. Okay, and he did the following measurement. He had a cat. The cat they gave him a bit of thing to make him calm, or she. I don't know whether it's a female or a male cat, but the cat was calmed down, and they put in a probe, one of these, gold filament covered by glass probes, in one of the neurons, in the visual cortex. The visual cortex is behind. In the visual cortex, this part of the brain that processes the information coming from the eyes. Okay? And then they turned a light on and off, so you have all of these 1 to 12 measurements. At the left-hand side of the measurement, what happens? You turn on the light and turn it off, so the cat sees the light. Okay? The cat says, I see the light. No, I don't think so, but I don't think the cat said that. But never mind. So the cat sees the light. And what's interesting, then you measure this particular neuron, which is in the visual cortex. What is the signal that results from that? And you see 12 experiments, and none of them are identical. Okay, so what you're seeing is what is the same everywhere is you see the pulses that you see, what they call the spikes, are approximately 70 millivolts, 70 millivolts amplitude. Okay. They go from minus 20 millivolts if you ground the cat from minus 20 millivolts up to 50 millivolts or something like that. Okay, the amplitude is approximately 70. Okay, and the shortest time between spikes is 1 millisecond, a thousandth of a second, which is much slower than the computers we use today, right? But this is our brain, so we have very slow computers compared to technology, to microelectronics. They go at gigahertz speeds, and we go at not even a millisecond, 1,001 kilobits per second at most. Okay, but the brain has different areas, and 1 millisecond inter-spike time is the shortest we can hope for, and the reality typically is around 10 times bigger. Okay, so we have a very slow computer, but it allows us to do things very quickly, actually, for the kind of things we're doing, like me talking right now. We're doing it very fast because we're processing a lot of things. And the reason why we're able to do this, of course, is because we have a lot of them operating in parallel. Okay, we have billions of them working in parallel with different areas specialized in different things. So this is the origin. These measurements are the origin of the random neural network, okay, which is my invention. So the random neural network, the initial papers are from the beginning of the 90s. And then, lots of applications and other results and generalizations and so on, mathematical generalizations are coming now. I even get, I see people in Russia, for instance. Yesterday, I saw a citation from Russia where they were doing some kind of generalization of the model. So people around the world, work on this for different reasons. Some just to do math and some to do something useful. But anyway, so what is this random neural network? I won't go through the math because it's probably not something that all of you are interested in. But basically, it's an n vector, n neuron system, okay, represented by an n vector of integers, where each integer represents the voltage at the neuron, the voltage that you would have measured at a neuron. And then you have spikes that are exchanged between these neurons, okay, and which either excite or inhibit the neurons where they go. Because in our brains, we have the spikes that you saw on the picture before, okay, the little spikes. Some of them are excitatory, and they will increase the voltage of the other neuron that received them. Others are inhibitory. They will reduce the voltage and make it less likely to operate. Okay, so this behavior leads to kind of a formal definition of what is happening in the network. You can define it mathematically, and having defined it mathematically, then you can write equations for the probability distribution, pk of tk. Small k is a vector of values, a vector of integers. And so you get the voltage of the whole network through in a probabilistic way, in a probabilistic formulation. And this then leads to so-called master equations. Physicists use these kinds of equations in statistical mechanics and in other areas. These are master equations for the random neural network. So you get a system of equations, which has then, the whole theory is based on these equations and proving that it has a nice solution, a very nice solution that you can then use for machine learning algorithms. Okay, so this is the whole story of the random neural network. And then you can say, well, how can you do gradient descent? And it turns out that for this system, just like for the backpropagation model, you have a very similar algorithm, although it's not the same mathematical model. It's not the same mathematics even. The other one is a deterministic for what you are using for the CNN or for the McCulloch-Pitts network, which I mentioned before. What you use in your black boxes is deterministic mathematics. This is related to probabilities, so it's a probabilistic model. However, the equations end up to be just like the previous one. It turns out to be, at the end, fixed point iterations, fixed point solutions of nonlinear equations, and inversion of matrices representing the weights in the network. Okay, so you get that. Now, and then you can, of course, represent your algorithm as, a series of steps, because that's an algorithm, and, so it becomes straightforward then to program this and to use it. Now, let's see some applications. In the remaining few minutes, I'll mention some applications. Some of them were mentioned by the person who introduced me so nicely. Thank you very much. Thank you for your introduction. For instance, cyber attack detection. So in cyber attack detection, you want to be able to detect attacks within milliseconds, literally, because if you if you say do it 100 milliseconds or 300 milliseconds later, it's too late. The attacker may have already succeeded in penetrating the system. Okay, so on the left-hand side, you have the neural network architecture based on the random neural network for doing this, and on the right-hand side, you have the numbers showing how accurate it is. Okay, accurate in doing what? In detecting attacks. Okay, and also in not saying there is an attack if there is none, which is very bad, right? Because if you do that, then it's like the story of the wolf. I see a wolf, I say a wolf, and the next time you say it, they say they don't believe you anymore. So the thing is, you have your false alarms must be small, okay? So what you're seeing here, the numbers may be too small for you to see on the board, but basically what you see is we have accuracies of the order of 99.78%. So high accuracies and very, very low false alarms of 0.002% false alarms and so on. So what we do is design systems which, and do these systems do what I had said initially, that they optimize and simulate? Yes. First of all, as you are designing the neural network, you are going to do optimization. What are you going to use as input data? You're going to use examples of real attacks. And with these, you're going to train your network, and examples of normal traffic with which you're also going to train your network. And then when you are running this, you're doing a trace-driven simulation. And what's the trace? The trace is the traffic coming in. And then this is answering yes, no, yes, no. It's been taught, it's been trained for this job. Okay, and the training part is optimization, and the testing part, where you're actually running it, is a trace-driven simulation. Okay, which comes back to what I had said a lot of these algorithms do. So this is one example, and all of this, of course, appears in journal papers or conferences, but mostly in journals, just like the rest of the work. And these are quite recent, as you can see. This kind of work that I do is also funded by the European Union through research grants or through PhD studentships. I have a new project now, just started on 1st of January in this general direction, but focusing on the cybersecurity of the smart grid of electrical systems. Okay? Another application is video compression. Okay, in video compression, how can you use a neural network? Well, you can build a neural network that takes a lot of a big picture and encodes it into a small neural network. Okay, and then your output must go back to a big picture because that's where people look. But in between, you have less data, and you transmit it much more efficiently. Okay, so this is how you do compression. And in compression, again, we have used a random neural network. Again, we do minimization and trace-driven simulation. Minimization, when do you do it? When you're training your neural network. With what do you train it? With real video. And when you test it, what do? You run real video, and now it's doing the work for you after having been trained. It's doing trace-driven simulation. So in this case, this picture here is important because along here, the x-axis, you have the degree of compression. Along the y-axis, you have the accuracy. Okay, so what you want to do is you want to have good accuracy, but for high compression. You want to shift to the right of the picture, and you want to remain in good accuracy. You see what's happening here. Suppose if this is the minimum accuracy that you want, you can go so far in the amount of compression. So these things are important because then you use your bandwidth in a network efficiently. Okay. Again, these are journal articles. Proceedings of the IEEE is the masthead journal of the IEEE. It has an impact factor of about 22, 23, 24, something like that these days, perhaps a little bit bigger. So these are, standard journals where we publish. This is work that we did, and it was a problem that was brought us by medical doctor Krishnan at Duke University. So he brought the problem to us and he said, look, I, as a neurosurgeon, he's a neurosurgeon. I, as a neurosurgeon, I get these MRI scans of patients, and I spend a lot of time figuring out if the cancer is bigger now than a week ago. Okay, because his patients are getting chemotherapy. And he has to not only see if the chemotherapy is working, if it's working, then the cancer is getting smaller. But of course, in a week or 2 weeks, it's gradually smaller. It's not such a big difference, okay? So he has to see that. And also, he has to decide if he's going to do surgery or not. And if he does surgery, he has to know exactly where. So for instance, here in this picture, you can see these are left and right, they're MRI scans with different modalities, T1, T2 images. And on the right-hand side, you see the exact localization of the cancer, of the tumor itself, okay? Because the tumor is typically surrounded by healthy tissue, which is, in addition, has some kind of inflammatory response to the cancer, but it's healthy tissue. So when the neurosurgeon decides to do something, he or she has to remove only, because more you take out of the brain, more trouble you're giving the person afterwards. So they have to minimize what they take out. And you need to be able to localize quite in a detailed manner what you think is really not you, but what your machine learning algorithm, AI, really thinks is the unhealthy part, the cancerous part, and what is only inflamed but healthy tissue. Okay? And this we're doing with a technique where we look at the texture. We don't look, because the shape is irregular. You can't say it's going to be this size, this shape. It's not going to be round. You don't know. The shape is unexpected. The shape won't tell you anything. What you need to do is look at the texture, at the detail interrelation between different cells in this area. And that you can capture through texture. And this is what we did in this work. What we did was we designed an algorithm which learned texture, and then we applied it to MRI. And this actually became a commercial product, because we sold it to Sandoz, which is a pharmaceutical company, because that prepare the chemotherapy medicine and so on. So for them, it's very important to evaluate whether their medicine is working or not. Yeah? Whether the drugs they produce are working or not. And they can see this through changes in size and shape of the tumor itself. So that's quite interesting. Finally, this was also related to textures, and the patent is up there. So we were using this algorithm for texture. And in this case, what we do here, everyone will agree that this texture on this the textures on this column are the same as the textures on that column. Everyone will kind of agree to that. But one of them is the original one, and the second one is what, after learning, reproducing by the algorithm. Okay, so we were able to show that this is really reproducing textures. Then you do statistical analysis and you say, well, this is really the same texture. So that was another piece of work, and of course, published as well. So I think I've given you I've tried to give you both a general view of the subject matter and a specific view of what the techniques are and what the methods are. And what I've tried to do especially is consider AI to be a balloon with a lot of hot gas. I've taken a pin and made a little hole in it for you, so that you look at it a little bit more like, what is it really and how does it work? Thank you very much. Sure. I think there's a question here.
Am I audible? I am Aditya Kumar, and is my voice getting clear? Sure. So my question was that one of the applications of IRM, as you mentioned, was cybersecurity, and in that you mentioned botnet, and it is specifically designed to. Yeah, sure. So it is specifically designed to handle millisecond rate attack, which in technical terms we call burst attack or hit and run attacks. To handle second. So can I directly call burst attack or hit and run attack?
It's not my fault.
Can I directly talk to you? Yes, so basically, my question was some attacks like stealth attacks and APTs, which are advanced persistent threat, which do not, as you know, have as a they are not a sudden surge in the system, but rather a persistent threat in such that the attacked party loses resources, or in a way that the motivation behind those attacks is to pass these systems checks. Also, my second question, I would just like to ask both of them.
The first was not a question.
So
It's what we call a statement.
yeah, so in that question, the exact question is that how can we design in this system to handle APTs, given that they are also no, in the umbrella of the cybersecurity?
I didn't understand. I understood your statement. I didn't understand your question.
Okay, sure. I will present in a very simplified fashion. This system can handle, sudden surges or burst attacks. Can it handle stealth attacks? And if so, how?
If you want to listen to my talk about cybersecurity, you should come to the National Computer Conference in Hyderabad in a couple of days. Okay, so I cannot today give a complete talk about cybersecurity. However, we have, of course, this is one example. It's not all of our work. So there are different ways to handle different types of attacks, and there are also some commonalities among attacks.
Yes.
And one of the things that you can do, for instance, in attacks is correlate what is happening at different network nodes and use that to determine whether an attack is going on. So it's kind of a complicated thing. So I don't want to go into the details because I think it would require, a different presentation.
I understand. Thank you.
It's a fantastic lecture. Thank you very much.
Thank you.
It's so great. I mean, you talked about the history of AI as well as where we are now. So I have two questions. The first one, is there a relation between LLM and neural networks?
Not necessarily.
No, it's okay.
No, because, ELIZA didn't use neural nets.
Right. But do some LLM use neural network?
Well, the thing is, I'm sure they do. I'm sure they do. They use a lot of things. I mean, it's kind of a system. So they'll use pattern matching, definitely. I'm sure they use pattern matching because they have to reproduce pieces of text which are recalled by other pieces of text.
Yeah.
When the prompt is coming in, you start recalling things from a database and so on. So I think they're doing all kinds of things, and they may use neural nets as one part.
Yeah.
Okay.
So it's like a black box, which is not very well understood from what I know.
I mean, it's an engineering black box, and the only thing that a lot of these people, I mean, the producers of these are willing to say is that it works most of the time. Okay, but of course there are big cases where it doesn't work. Plus, there are fundamental problems, which are the following. Just a couple of days ago, a journalist said that this appeared in the Washington Post or something like that. I have the full text on my computer. The journalist said, well, I did the following thing. I wrote an article saying that I had run a competition for the fastest sausage eaters in the world. And then I named myself as the fastest sausage eater in the world. And then I named this person, this other. I asked them, "Can I use your name, etc." So he named other people as not so good as him, but also very fast sausage eaters. And he put this online. Okay. And then a couple of days later, and of course, he is not this. This is all nonsense. A couple of days later, he ran ChatGPT and said, "Who is the fastest sausage eater in the world?" It came out to be himself, and the other people were also listed. So what I mean is that it's a storage system, right? So you can add nonsense to the storage system, and this is a danger because with the press, for instance, a newspaper, there's a law about the press. I mean, if you're in India and you write an article in the newspaper and you insult someone, you can be prosecuted, right? Well, for ChatGPT, there's nothing like that.
Yeah.
You can produce anything, and it's fine.
No, not anything. Most of the time, my interactions with LLM are a lot more sensible than with my friends. So that's a failing of the humans, but that's okay. Second question. You're looking at the gradient search, right? So gradient search is very local. How do you cast the net very wide?
Well, there are
So
all kinds of standard techniques which are in these boxes, which is you restart. What you do is you go down, then you heat it up. By heat is you create like a physical temperature,
Yeah, I got
which means you change exactly. So you move yourself out of the local minimum and you start again.
So as you add a lot of noise,
You add noise,
you
and so
jingle,
there are
right.
all these noise. They call them diffusion
Yeah,
learning.
But can you have a net which is wide right in the beginning, rather than after you get trapped in a minimum, then you jingle it and then you get out from there, right? That's one way. That's very classical. Even I used it in my master's thesis. But like when you start your search, is there any way to tell what's a good place to start the search?
Yeah, there is, and that is to use classical optimization to produce a guess of an area, of a set of parameters, of a ballpark area where you expect the minimum to be, and that requires a simplified model and optimization.
There used to be okay. This was long years ago.
And you
By
might
the way,
use combinatorial
by the way,
optimization.
I just found out we have something in common. Our birth date. I'm 15 years younger, but it's the same birth date, 22nd August. Right? I saw in Wikipedia.
Fantastic.
Okay,
There must be
fantastic.
something to that.
There must be something to that. So now, I was saying, so I was when I was doing a PhD, I was using some stuff which is called Minkowski functionals, which is that you do kind of so basins of attraction to the fixed points. So take some domain and then say, look, is it still going to this minimum or is going somewhere else? So I don't know if people are using some like
Yeah, they're using all kinds of optimization simplifications. Yeah, I think all of these things are being used.
Fantastic. Thank you.
And
So
with
much.
respect to the noise, there's something fashionable right now called diffusion learning,
Diffusion
which is
learning.
basically you add a
The
diffusion
noise.
process. You
Wow.
add a diffusion process.
I wish I started working this area 15 years ago. I already knew all this 30, 40 years ago.
Well, yeah, exactly.
late
That's
now.
why I took the balloon and make a little hole in it.
So good. Thank you so much.
May I ask a question online?
Coming. We are coming, but we have a question by Professor Mande, sir. He is online. So, sir, can you unmute and?
Yes, I have unmuted. Can you hear me? Can you hear me?
Yes.
Yes, Professor Gelenbe, it is a delightful talk. Thank you so much for that.
Thank you.
What I was wondering was, in the topology of these random neural networks, do they resemble any of the graph theory when we call random or small
It's
world
very difficult to hear you because of the echoes. We have a system here which is producing echoes.
Oh God. Is it similar in topology to the graph theory networks, what we call random or scale free or small world? The topology is very different.
No, the topology is arbitrary.
So they're not, I mean, they're random, but they're not small world or something. Would you qualify them as small world networks? Not really. Would you qualify them as small world networks or not really? Okay. Thank you. Thank you.
Uh, Excuse me, sir. Good morning, sir. Good afternoon, sir. My name is Shivam. So, I want to ask you two questions. First is, what is the specification of random neural networks? There are DNN is there, CNN is there, ANN. All models are there. Like, what is the specific what random neural network is specialization?
I said either you might represent it in classical mechanics or you might represent it in quantum mechanics. Well, classical mechanics will work at a certain scale, but you need quantum mechanics to deal with a different scale, to deal with reality at a different scale. Now, in the random neural network, if you want to go down to the actual representation of the neurons that are in you, I designed it especially for you personally, because they correspond to the neurons in your brain and even in mine. So that's the idea, the whole idea of the random. In fact, we did at the beginning of the model, I didn't talk about this, but what we did was we took measurements on collections of brain cells, and we did the mathematical model for them, looking at rats. Because in the lab next door, there were negative to express the fact that they are excitatory or inhibitory.
Yes, sir. On the other hand, we also have an attention which works on context. Now, speaking biologically, if a human is provided with some kind of a context about something, anything, then various places are there where the performance increases.
see what's happening. Okay, what it does is it has inhibitory projections. The vision system has an inhibitory projection on the rest of the brain, and it removes the oscillations. Now, with a random neural network, you can perfectly well represent that. But your question was very general, but I'm just giving you a specific answer. Because, when you talk about biology or things like that, what I learned is that in biology, it's figured out everything. It has an answer to, that's why we are here today. That's why our species has survived. And like many other species have survived, because we have, our system has found a solution for a lot of these problems.
Thank you, sir.
You're welcome.
Thank you, Professor.
The funny thing is, I'll just add one more thing about that. At one time in my work, I was talking a lot to biologists, neuroscientists, a lot. So I would say, can it do this? They would say, yeah, I know a neuron that can do that. So the variety of things, of solutions that biology has found is incredible, because they have something specific. Recently, I was looking at a worm, a special kind of nematode. And they're doing some experiments on the worm. They puff some air on the worm, and the worm changes shape and protects its head. And they found that this was done by 7 neurons. Well, the poor worm only has a few thousand. Okay, and seven of them are specialized in doing this business. But they've been designed by nature to have the topology and connections and the reactions, etc., to do exactly that. Okay. Another example I saw was the tail of the fish. Okay. Again, when I was beginning with these models, I was visiting a lot of neuroscience labs, and I visited a lab in a place in Paris called the Collège de France, where it's kind of a very special institution. And there was a Henry Korn was this biologist. He died since then, and he had one fish, a big water tank, one fish, about this size, and a wire, an electrode. And he had electrodes in the ear and electrode in the tail. Okay, and he had shown that every time you do this, there's a random pattern of spikes that goes to the tail. Why? Because the fish has been designed to move differently every time. Because if the fish moves the same way every time, the next time they will eat it. Because usually a noise is a danger. So the tail moves differently through a random sequence of spikes. And the fish takes evasive action, but not twice the same, because he was doing with a fast camera looking at the fish. So I'm saying that, and this was context awareness, right? I hear something, I have to do something different now, next. But he didn't even have to think, because this was done automatically by the system the way it had been designed. So you see these examples in biology, which are extraordinary.
Thank you, Professor, for the wonderful lecture. I mean, it gives a very different perspective to what personally I think about AI. I am Vivek, and I'm doing a post-graduation in computer science at Amity University. I want to ask something really different here. When we talk about humans, we have a decision memory, like into that aspect that these AI agents have some kind of a decision memory, that this information should not pass on to this information to the person, or we can say like they can have empathy with the AI agents.
Yeah, actually, this is a form, what you say is a form of not attack detection, it's a form of intrusion detection. That is, you can have one neural net that looks at who you're talking to, and a neural net, another neural net that is answering questions. okay, or another AI system that's answering questions, another AI system which is looking at. So the one that is looking at that person may answer saying, "Don't do this." But this is exactly what we do a lot of the time. When we're in the street, someone wants to talk to us. We have a reaction. Some people we will talk to, and some we will not, because we can sense a danger, right? And these are not all the same part of the brain. You have specialized parts of the brain. I mean, there are special parts. We have emotional parts, for instance, where the talking part is one, and then we have emotional parts, which are other, which guide the other side. So yes, why not? You can have a system which includes observation and choice, another part which is doing some useful action, which is like talking, answering a question, and so on.
Thank you.
We do that, and there's no reason why you can't design, say, a robot that does that, or even a computer system that does that.
Thank you, Professor.
I can stand.
Thank you so much, sir, for making us understand the complex topics of algorithms and AI. Also, listening to your lecture today, and also telling about the experiment of the visual cortex of the cat. It was really interesting. So, neuroscientist. So, that was really amazing. And
I didn't talk to you about the whisker of the rat, which is even more funny.
we can have the discussion over the tea time for sure, sir. Thank you.
It's a true story. Whisker of the rat.
We will have the discussion for sure, sir. And I hope that this engaging talk will truly inspire and ignite the curiosity among our young future generation of our nation. Thank you so much, sir. I now request, thank you. I now request Professor Ashutosh Sharma to please come up on the stage and present the honorary memento to our distinguished speaker for today.
Honorary memento, but the memento to honor.
That's interesting. I looked at it before the talk. I looked at it. It's very interesting.
Global optimization.
Wow. The globe is optimized.
Additionally, it is my privilege to mention that Professor Gelenbe is our INSA Foreign Fellow 2026, and I request our former president, Professor Ashutosh Sharma, to present the fellowship scroll to Professor Sami Erol Gelenbe.
So we also have Dr. Mande with us.
Yeah.
So he can symbolically present it, and then I'll physically present it. Yeah.
I request Mande sir to please read the fellowship oath to Professor Gelenbe.
Yes, thank you. Professor Gelenbe, would you be kind to repeat after me?
Yeah.
Oh, okay.
Yes. As a fellow of the Indian National Science Academy,
I have signed the book, I think. Oh, sorry. As a fellow of the Indian National Science Academy,
I shall follow the code of scientific ethics,
I shall follow the code of scientific ethics,
maintain integrity
maintain integrity
in research
research
and
and publications,
uphold the cause of science
uphold the cause of science and the
and the
dignity of the academy,
endeavor to be objective,
endeavor to be objective in my judgment, and strive for the enrichment of human values and thoughts.
Professor Gelenbe, in the name and by the authority of the Indian National Science Academy, I admit you as a fellow thereof. We are greatly pleased to have you as a foreign fellow of the Indian National Science Academy. Congratulations.
You see, it's all very serious affair. We repeat it twice, then it solidifies.
That's why the echo is not, it's not an echo, it's for twice, you understand better. It's ML. Reinforcement learning. It's not reinforced learning, it's forced learning. Thank you.
Thank you so much, sir. I also thank Professor Shekhar Mande, who has joined us online. And I also extend my heartfelt gratitude to our honorable speaker today. Yeah. As we come to the close of this enriching session, it is my pleasant duty to propose the vote of thanks. I sincerely express our deepest gratitude to Professor Sami Erol Gelenbe for delivering an illuminating lecture and sharing his profound insights on the computational foundation of artificial intelligence and the random neural network. I extend my heartfelt thanks to Dr. Shekhar Mande, President, Indian National Science Academy, and Professor Ashutosh Sharma, former President, INSA, for their gracious presence and for warmly welcoming our distinguished speaker today. My sincere appreciation to the fellows, members of the scientific community, students, and all participants for their enthusiastic presence and active engagement. I also acknowledge the dedicated efforts of Dr. Brijesh Pandey, the organizing team and staff of INSA for ensuring the smooth conduct for today's program. The audiovisual setup was a bit not acknowledged by our setting for today, but yes, these kinds of technological glitch occurs. So we accept that and we move ahead. And thank you all for your cooperation. I now request everyone to please rise up for the national anthem. I request everyone to please move for the evening tea and followed by the group photograph session. Thank you so much.
Thank you.
Thank you for your presence. That was really interesting.
Thank you for your.
It was on a very short notice, and we have a National Science Day also.
Yeah.
So we are completely occupied with that.
Of course.
28. Should have
Thank you for everything. Thank you. And I'll place it in